Hi there, I'm Ayaan. I'm 14 years old, and for the past couple of months, I've been researching into DNA Origami, which is the nanoscale folding of DNA to create these 2D and 3D objects at the nanoscale. And while this might just sound like another buzzword, we can actually use this technology to impact billions. We can allow delivery of cancer medications to just be 10 times more effective. We can incur the mobilization of enzymes. We can allow certain reactions in the body to occur better than they are currently, and we can also allow self-assembly. So pretty cool. And when looking at all these things, I knew that this technology had humongous potential, and I just wanted to get hands-on and build something. And so for this project, what I created was a 3D DNA Icosahedron, which looks something like this. And so what we'll do today is just walk through the steps of how I was able to create this, and also talk more about how we can use DNA Origami in real-world scenarios. Hope you like it.
So I started off by opening a program called CAD Nano. And what I did in this program was basically represented the geometric template so that each of these circles was a double helix. And what you see on the side is that the blue arrow and the square just represents the double helix. And we can extend these to have the sequence be as long or as short as we want, depending on what face we're creating. So each of these hexagons is one formation of a long sequence, and each of these specific circles that I'm clicking on is a smaller strand of the longer sequence. And so in the end, what we're going to do is we're going to take all these hexagons and then merge them together to end up creating that one big DNA icosahedron. So what I'm going to do here is basically just create all the nucleotide sequences and specific strands that I need to end up creating the DNA icosahedron.
Okay, so while waiting for the geometric template to be finished, let's talk about the use case of DNA Origami. Well, right now researchers are using it mainly for better delivery of cancer medications. And so what does that look like? Well, since we know that in cancer drug delivery we use our veins as highways and deliver the medication to all parts of the body, we know that that's the reason why they don't work, because they also harm other parts of the body and other cells that we need to grow. Whereas with DNA Origami, now what we're looking at doing is having these small little DNA boxes hold the drug and then deliver the drug using the veins as highways only to the specific place where the cancer cells are, and we can detect the cancer cells based on certain biomarkers. And so now, wherever the cancer cells aren't, we just have these small little boxes of the medication not deliver the medication. They'll just stay there, and over time, nothing will happen to them because they're so small, they'll literally have just zero effect on the patient. So basically, cancer drugs, but 10 times more effective. Okay, so now let's just get back to the DNA icosahedron.
What we can see here is that we've already auto-stapled all the strands. And so what does that mean? Well, it means that I've already had the specific smaller sequences inside of the circles and the hexagons been put together. And so we're only going to look at one portion of this. And if we zoom in, we can see that that specific section isn't connected to another hexagon, at least not yet. If we go back to the hexagon, we can also see that we have these numbers on the left-hand side. So 90, 91, 95, etc. But in the hexagon, 90, 91, and 95 are together. And so you must be wondering why that happened. And that's because we only want number 90 to bind to number 91, 95. When we click on the strand, we can see that only 91 and 95 appear because those are the only two strands near to it. So those are the only ones that it can bind to end up creating the longer strand. And so what we can do is create merged nucleotide sequences in between these smaller hexagons so that the overall DNA icosahedron can be much more stable. The binding affinity can be much stronger. And so if we zoom out, what we can see in the bigger picture is that there's cross nucleotide sequences between hexagons, merged ones. And so in the end, what we did is just merge nucleotide sequences between hexagons in the geometric template to create hexagons that are merged in total to end up creating the DNA icosahedron.
Thank you so much for watching the video. If you want to know more about what I'm working on, you can check out my LinkedIn and my Twitter, and look forward to more videos coming out soon.